And the hour has pretty much arrived. I'll wait another minute for the remainder of the peak. Of course, you can't tell. It's not like the murmur subsides because we can't really hear the murmur. Not yet, anyway. The chats and the Q&As haven't started yet. Good evening, good afternoon, good morning, good everything to the world of quantum devices. This is the last session of the Quantum Devices workshop of the Simons Institute of the Quantum Waves program for computing. And I'm pleased to chair the next two presentations by distinguished physical theorists who work on innovative modeling of superconducting devices and are studying different aspects of how they can be brought to a new world. We've heard quite a bit this week about how existing quantum superconducting devices are already influencing our world of quantum computing. So let me begin by introducing Alexandre Blais, professor of physics at University of Sherbrooke and director of the Institut Quantique there. And he will give us a lecture on quantum computing with stabilized cat qubits. Alexandre, take it away.
Okay, thank you, David. Thank you for giving me the opportunity to speak at this conference and for the Simon Institute for adapting to the new situation so rapidly. So thank you, everyone. So today I'm going to talk about quantum computing with stabilized cat qubits. And this is work which was really started and led by Shruti Puri when she was a postdoc in Sherbrooke. And she has continued to play that role now that she's a postdoc at Yale with Steve Gervin. So since the topic of my talk is qubits beyond the Transmon qubits, beyond the current standard qubits, standard superconducting qubit, I thought I would take the opportunity to say also a few words about some new results that were obtained in collaboration with Andrew Hauk, Jens and David Schuster on the 0-pi qubit. In Sherbrooke, that work was led by Agustin Di Paolo. So we've heard about superconducting quantum processor already during this week, but it's probably a good idea to say a few words about, again, the basics of how they work before moving on to how are we going to try to improve them. So today, all of the superconducting quantum processors that are being studied share a few, share many ingredients. To start with, all of them, or most of them, are based on so-called Transmon qubits, which are either represented by simple two-level systems. And all of these Transmon qubits can be individually controlled with microwave pulses to realize X, Y, or Z gates. And then to make these qubits interact or to read out these qubits, you embed them in a microwave cavity represented here by the two mirrors. And so this cavity plays many roles. First, you can send a microwave tone at the input point of the cavity and collect what comes out. And that the microwave tone coming out of the cavity will in fact carry information about the states of the qubits which are inside the cavity, therefore allowing you to do a qubit readout. Moreover, this cavity can be used as a form of quantum bus to mediate interaction, mediate entanglement between different qubits. For example, if you prepare some interesting states of your first qubit, then you can transfer this state to a microwave photon, to an excitation of the cavity field. And this excitation can be reabsorbed by the qubit, which doesn't have to be a nearest neighbor qubit. And in this way, you are able to entangle the different qubits. Okay, so the transmons are embedded in some type of microwave cavity, which allows you to do readout and gates. So that's one variation on superconducting quantum processors. Another variation looks a little bit more like this, and this is what we've heard from the Google group earlier this week. In this particular realization, what they do is they again use Transmon qubits, which are again read out by microwave resonator, but rather than using cavities to mediate interaction, these qubits are coupled through some other couplers. In that particular case, these couplers are in fact other types of Transmon qubits. Okay, so that's the state of things in superconducting quantum processors. And of course, by now we can scale this to several tens of qubits and operate them coherently to do interesting computations. But of course, as we scale up, it's important that we look at the next challenge for the field. And that next challenge, I think we can all agree, is quantum error correction. How do we bring in quantum error correction? Because simply brute force scaling these devices is probably not the solution. And this is where it's getting a little bit scary when you think about what quantum error correction means and requires. For example, if you are interested in factoring a 600-bit number, this will take something like 1,000 logical qubits. And if you encode these logical qubits in the surface code, using the surface code, that may mean that you need something like 10 to the 6 or 10 to the 9 physical qubits. That's quite daunting. That's, of course, quite challenging. And so what that means is that we need better physical qubits. We need to improve the quality of these qubits to make sure that, the overhead that is required is not too large, and also improve the codes themselves. The surface code is quite interesting. It's a great path forward at the moment. It might not be the solution. It might not be the only approach. Okay, so if we want to think about improving upon the qubits, it's important to look at what is the current standard qubit, and that's the Transmon qubit, which is used again by Google, IBM, and many academic groups, of course. And so the Transmon qubit looks something like this. So it's simply a Josephson junction, which is shunted by a large capacitor. And so it looks something like this. If you take an optical image, this is just one type of realization of the Transmon qubits. You will see in the literature Transmon qubits looking very differently than that, but they share the same common simple circuit. So this circuit has several advantages. This is why it's being used so widely. And one of these is that it has pretty good coherence times. Its coherence time are relatively long. And so if you look at the evolution of these Transmon-like qubits over the years, in green, their T2 time, or if you want the typical time for a phase error to occur, and in blue the T1 time, or if you want the time, the typical time for a phase flip error, bit flip error to occur. These times have increased quite dramatically since the first experiment by Yasu Nakamura in 1999, where these times were sub-nanoseconds. In fact, it's quite interesting, I think, to plot this on a log scale where you see the, sorry, I'm trying to reconnect my iPad. You see, okay. Just 1 second. Okay, so I've lost my nice pointer. No problem. So you see here that there is some interesting rate of improvement of these qubits over the years. But okay, of course, in the last few months, we've been looking too much at exponential curves. So let's not dwell too much on this anymore. I will rather say that the Transmon qubit is interesting also because it almost always works. It simply works. You build them and they work. And so we know, for example, from the Google work, the chip really had 54 qubit, but only 53 of them was working. One was not working. But what we've learned in Monday's talk is that the problem was not with the Transmon qubit itself, was within some external connection to that Transmon. So you can build several tens of these Transmon qubits and they will simply work. They're also, of course, also quite simple, just a junction shunted by a capacitor. Okay, but that being said, so these advantages explain why the Transmon is being used so widely. But what we've seen over the last 20 years is some kind of what you could call qubit Darwinism, where initially there was several types of superconducting qubits that were studied, and now we've seen a strong focus on the Transmon. And so this has certainly led to improvement in the short term and in the midterm. And this is what we're really seeing here. So this is really the effort of several groups worldwide allowing for these improvements. But maybe by focusing so much on a single type of qubit, we might have lost some advantages in the long term, because maybe the Transmon is not the final qubit that will be used in a quantum computer. The Transmon might not be enough. And we've seen recently a resurgence of different types of more exotic qubit, for example, the fluxonium, the 0-pi qubit, and the bosonic qubit, or the cat code qubits, which I will speak more about today. But before we go into the bosonic qubit, let me say a few words only about the 0-pi qubit. So the 0-pi qubit is quite an interesting device, I would say. This is one of these candidates that are beyond the Transmon. And so this was first introduced by Kitaev and then studied most closely by Brooks, Kitaev, and Preskill in 2013. And so this is what it looks like. So you have, again, capacitors, junctions, and now, in addition, inductors. And if you look at this device in your ring, for the moment, the inductance, you see something like looks like a Transmon. So hidden in this 0-pi qubit, there's a Transmon-like qubit. There's a Transmon-like degree of freedom. Now, if you ignore rather the capacitances, you see a loop. And for some of you, that will remind you of a flux qubit, or more precisely here, something that we would call a light fluxonium qubit. And so really, in the 0-pi qubit, there's different species of qubits that are hidden. There's different degrees of freedom. And because you have these different degrees of freedom, you can optimize you have more flexibility in optimizing the system, such that you can find parameter regimes where T1 and T2, the error rates, the typical times for errors to occur in this qubit, are exponentially suppressed. That's quite interesting, because what we know is that in simpler devices that have a single degree of freedom, such as the Transmon or the fluxonium by themselves, something like this would not be possible. But that comes at a price. I mean, this device is challenging to realize. For example, these inductances are not made of simply small wires, but are made of arrays of Josephson junctions that can have hundreds of junctions, something like 200 Josephson junctions. Moreover, because the qubit is protected against errors, it's also, in a sense, protected against gates. It can be difficult to enact logical gates between two protected states. And if you want to learn more about this, I encourage you to look at these papers by Agustin Di Paolo and colleagues, where we have looked at these questions. So quite recently, this qubit was now realized in the group of Andrew Houck at Preskill, at Princeton, where, so this is a picture of what it looks like, where you see Josephson junctions and these thick wires, which are the superinductances made out of hundreds of Josephson junctions. And so for this very first device, what we have observed is T1 and T2 times that are quite good. In fact, the T1 time for this very first 0-pi device is as large as 1.5 milliseconds. So that's an order of magnitude larger than your typical best Transmon. And the T2 time is not as impressive, but is still very respectable, 26 microseconds. And it's important to understand that this is a first device. That's a first realization of these ideas. We're tempted to compare these numbers to the best Transmons that are out there, but we have to remember that these Transmons are the results of more than a decade of improvements by tens of groups. If the first Transmon had such impressive results, that would have been quite something. So we're quite happy with these results, and we think that the 0-pi qubit is very promising. Okay, so the 0-pi qubit is one of the candidates to give better physical qubits. Let me now introduce another type of superconducting qubits that could play this role. And that will tie in now with also better codes. That's the concept of cat qubits or bosonic codes. So what we've come to understand as a field now is that quantum error correcting codes are central to quantum computing architectures. Most quantum computers will spend probably most of their clock cycles actually doing quantum error correction. So while at the moment, most of the error correcting codes have been developed without thinking too much about the hardware, it's probably time that we start developing codes with a specific hardware in mind. And that's the general concept of hardware efficient quantum error correction, which is getting more and more traction in the field. So hardware efficient quantum error correction should be contrasted to generic error correction, where you take a bunch of physical qubits, here 9 physical qubits, and you encode a single logical qubit. So you encode logical qubits in the subspace of multiple physical qubits. And again, typically there's no assumptions about the underlying hardware. So there might be some errors that are unlikely, for example, in your hardware that you might be correcting with your code. And as a result, you might be using too many physical qubits. You might be using a larger overhead than strictly necessary. So here comes this concept of hardware efficiency. So here the idea is to encode logical qubits in a subspace of one or a few physical systems, but really try to exploit our understanding of the underlying hardware. What is the error model for this, for our hardware, and how can we tailor the code such as to take advantage of this error model, with the goal, of course, of reducing the overhead in qubits and gates and measurements. Okay, so now that we have this in mind, this goal of achieving hardware efficient quantum error correction with superconducting quantum processors, let's go back to such a processor and look at the different components. And what is the error model for these components? And what would be the best component to use as the carrier of quantum information? So let's first look at the transmons. So what are the errors that occurs in transmons? But I've already mentioned this. You have relaxation, characterized by the sigma minus operator. And then the timescales are given here, something like a few tens to a few hundreds microseconds. And there's phase errors with timescales which are linked to the T1 times. So there's 2 types of errors, and the timescales are at best 100 microseconds or so. We can also encode quantum information in the electromagnetic field, in this cavity, in photons in this electromagnetic cavity. And in that case, what is the error mechanism? Well, it's a simple error mechanism. It's simply the loss of photons, the loss of a single photon, one at a time. And that's characterized by the operator A, which removes a photon from the cavity. And the time scale for this, for high quality cavities, can be very large, even larger than a millisecond. So what we're learning from this is that the cavity in cavity QED has the simplest error model. To a very large extent, there's a single error channel, that's single photon loss. And its quality factor is higher than that of transmons. And so that suggests that maybe we should encode quantum information in that degree of freedom rather than directly in the transmon. And that's really this idea of encoding qubits in oscillators.
Alexandre,
so the first idea is...
Yeah. Alexandre, there was a small question which maybe can be dealt with quickly. It was already, though, 2 slides ago, you used the phrase exponential suppression of errors, I guess. And the question, yes, quite reasonable for a mathematical institute, is exponential in what? Maybe the answer is you'll get to that, or it'll become clear in some of the examples.
I will, yes. Okay, so I will have a specific example of exponential suppression of error in a minute, but for the Bosonic code.
Yeah, that should be fine.
I will come back to that in a second. So thank you for, don't hesitate to interrupt me. That's great, thank you. Thank you for the question. So as I was saying, so there's a general idea of hardware efficient encoding of qubits in oscillator. And this idea really started again in the early 2000 by Gottesman, Priskill, and Kitaev, who introduced the JKP code, which has been realized since in trapped ion and superconducting qubits. Other types of codes are the binomial codes and the in coherent state-based codes or cat state-based codes. And for those that are interested in hearing more about that, you can consult a nice review by one of the conference organizers. And today I will focus on coherent state-based codes or cat state codes. I understand, however, that maybe not everyone is familiar with coherent states, and especially coherent states of the microwave field. And so for the physicists, that will be, of course, well known, but it's not only physicists listening, or at least there's not only physicists listening into this presentation. So to explain this concept, I will use what some will take as a bit of a silly example, but I think that the silly example works well. And so this is my example. So this is a very familiar object, not the turkey in the microwave, but the microwave itself. And so by looking at this, we can understand exactly, I think, what I mean by coherent states of the microwave field. Why? Well, here you have a microwave cavity, which I represented before by these two mirrors, but now it's just the cavity of your oven. And rather than putting qubits in this cavity, we put turkeys. Well, maybe I don't do that, but maybe apparently, according to this picture, some people do that. And here you have a source, okay, which you use to inject a microwave field inside of your cavity. And so if there was no food, no turkey, you would get some amplitude of the field. But of course, some of that amplitude is being dissipated absorbed and dissipated by the food, and that leads to a lowered amplitude. Okay, so what we know now is that the amplitude of the field is an important characteristic of the field, of what I'll call a second coherent state. There's a second important number, and that's the phase. So what we know is that, of course, there are cold spots when we cook food in the microwave, and that's why there are these turntables to avoid these cold spots to be at the same place. And that cold spot is simply a manifestation of the fact that the field of the microwave oven has a well-defined phase, and as a result, points where there's simply no amplitude, no power of the field. And so rather than turning the turkey around, what you could imagine doing is changing this phase. And so if you could move this phase around, well, you would have you would move your cold spot and therefore cook your turkey beautifully. And so now we have two numbers to characterize the field, the amplitude and the phase. And that's what we call a coherent state. A coherent state is a state of the electromagnetic field which has a well-defined amplitude and a well-defined phase. And this I can write in terms of real and imaginary parts, x plus ip, which we call quadratures and are sometimes called I and Q in microwave engineering. And generically, we call this alpha being a complex number. And now this is great. I can plot this coherent state in the XP plane, in the quadrature plane. And so, of course, if the microwave oven is off, I just have a blob in the center of phase space of this quadrature space. Now, as I turn on the microwave oven, there's some power that is being built up. Now I assume the phase to be 0, just for simplicity. And as the food is absorbed, that power is lowered. And what we see here is that the point where this coherent state will stabilize is the result of a competition between two things. How much power are you putting in and how much damping is there? And the ratio between these two quantities will tell you exactly where this coherent state will end up. Okay, so what we've learned is that we can stabilize coherent states by opposing two things, microwave power and damping. Great, but what I would really like to do now is encode quantum information in these coherent states. I would like to call the qubit state 0 the alpha state, the state on the right. And I would like to call 1, the logical state 1, the state with the same amplitude but opposite phase, minus alpha. Of course, now what that means is that I need to prepare superposition of 0 and alpha, and using damping doesn't sound like the best idea. And so what I'm really looking for now is for a way to stabilize coherent states without using damping. I will need to have this kind of opposition between two forces, but it should not be damping in something else. Okay, so we will come to that in 2 slides. How can we stabilize coherent states, and in fact superposition of coherent states, which we call cat states, without using damping. Okay, so I hope that this example was clear enough, and sorry for the turkey. Before moving on how to actually stabilize these states, I think it's useful to again think about why is it that we want to use these states and what is interesting about these states. So there are two properties about these states which are in the box here, which are crucial. The first is that these two states are not quite orthogonal. They are in fact quasi-orthogonal. And so that means that for large enough alpha, they are, we will declare them to be orthogonal enough. And then for this reason, we can encode quantum information between in alpha and minus alpha as 0 and 1, because the overlap between these two states is in fact very small, exponentially small. The second crucial property is that coherent states are eigenstates of A. Remember, A was the photon loss operator. Acting on a cavity with A removes a photon. And that was the main error mechanism, remember, for a photon. And so what we're learning now is that acting on A on a coherent state leads almost to a trivial, doesn't change essentially that state. So that's very, very good news. The main error mechanism has a very simple action on our logical states. Okay, that means that I can encode some qubit. I have this Bloch sphere where I will declare the 0 and 1 to be the north pole and the south pole of this Bloch sphere. And what I would like to do is, of course, avoid any transitions between 0 and 1. I would like to avoid bit flips. And this is the exponential suppression. That's one example of an exponential suppression. I can compute the rate, 1 over t1, for these bit flips. And I can compute this using the so-called golden rule. If you're not familiar with that, that doesn't really matter. What is important is that you need to compute this expectation value. And you find that this expectation value decreases exponentially with the size of alpha. Okay, and so if you make alpha large enough, you can make the bit flip rate essentially vanish. This is great news. If for large enough alpha, we have a qubit which doesn't flip. However, there's no free lunch, of course, here. This is not a quantum error contained code. This is just a qubit. And so, of course, that cannot protect against all errors. Here, I would really like also to be able to prepare a superposition of these plus and minus alpha states of 0 and 1, which are, again, cat states. And so I need to look at what is the rate of phase flips 1 over t2. And here, in that case, the conclusion is not so good. While t1 was going down exponentially fast with the size of the cat, alpha squared, we find that the phase flip rate increases with the size of the cat, with the size of alpha. So that could be seen as bad news, but the good thing is that while this is going down exponentially fast, this is only increasing slowly in a polynomial manner. And so what this means is that we have a qubit which has a biased error model. Bit flips are extremely unlikely, but we will have to deal with phase flips. Okay, so now I can really think about the different types of encoding where I don't have to correct for all type of errors. This is extremely unlikely. I only have to focus on this. And because this one is only increasing slowly as this one is going down exponentially, I can always win. Okay, and that's the situation that I would like now to explore. But first, we have to understand how it is possible in superconducting quantum circuits to prepare these interesting states. I've already said that we can prepare these interesting states by opposing microwave power and damping, but this is not what we want to do here. We want to use something else. So now let me jump a little bit on the physics, a little bit more of these microwave circuits. So there'll be two Hamiltonians on this slide, but we'll be mostly done with Hamiltonians after that. So the physics I would like to explore is the physics of what we'll call stabilized Kerr cats. That name will be justified in a minute. So the main player here is, of course, the microwave cavity, which I represent since the beginning as two mirrors that are facing each other. But in practice, they may look something like this. Some of you are more familiar maybe with the 2D type transmission line resonators. That's another approach to realize resonators for microwave photons. So this is simply a block of aluminum, which has been cut in half, machined such as to create a hole there. And if you bring these two pieces together, you have a cavity in the middle, which is a few centimeter by a few centimeter. And these wavelengths corresponds to microwave frequencies. So you can store microwave photons for up to a millisecond or more in these cavities. So extremely high quality factor cavities. And these connectors here, these coax cable connectors essentially, are used to input microwave power and collect the microwave power that comes out, for example, for a qubit readout. Okay, so before stabilizing the stabilizing cats, it's worth looking again at the same old stabilization of a single coherent state without any turkeys here. So what we have without any microwave power in the quadrature plane, in the phase space, we have a coherent state representing vacuum at the center of phase space. Now, if I inject some power, I will, as I explained before, displace this field up to some value that I've chosen here to be alpha equals 2. Again, this is a competition between microwave power at input and damping. If I change the phase of the microwave field, I can stabilize minus alpha equals 2. And so what is the Hamiltonian that corresponds to this? This is it. That's a simple enough Hamiltonian where the first term gives me the Hamiltonian of the free cavity. Omega r is the frequency of the cavity. A dagger counts the number of microwave photons or photons in the cavity. So this is just the energy of the cavity. And that term represents the drive. So for those who don't like Hamiltonians so much, there's a nice, convenient way to draw these Hamiltonians, something which is called a metapotential. And that's quite useful because I can simply draw what this Hamiltonian looks like, and I can interpret this metapotential usually quite easily. So this metapotential is obtained simply by replacing A by the operator A by a complex number, x plus IP, and A dagger therefore by x minus IP. And the Hamiltonian H now becomes what I'll call the metapotential H of x and p. And I can plot this metapotential as a function of x and p. Here I'm plotting this at a cut at p equals 0. And what you see is a straight line. Okay, not so interesting. But what that means is that if I start at x equals 0, so the vacuum state I'll represent by this ball, which is sitting at x equals 0, but this ball will just roll down the potential. And the slope of this metapotential is simply given by the single photon drive strength. The more the higher the drive strength, the microwave amplitude, the more this slope becomes abrupt. And again, there's a counteracting force with single photon loss, which will lead to stabilization at some point. Okay, so that's easy enough, I hope, to interpret this potential. But this is not what I want to stabilize. I want to stabilize both alpha and minus alpha. And so really the metapotential that I want should look something like this. Because if I start with a ball at x equals 0, it will roll down in a quantum superposition of both values, therefore preparing and stabilizing the cat state. So this is what I would really want. And so in my opinion, one of the amazing things with superconducting quantum circuits is that I can draw the metapotential, a metapotential like this that I would really like to achieve. And then I can figure out what Hamiltonian corresponds to that metapotential. And then I can say like, okay, well, what is the device that corresponds to that in the lab that corresponds to that Hamiltonian? And the amazing thing is that these mappings are very accurate. The metapotential to the Hamiltonian is of course exact, but from the device Hamiltonian to the actual device in the lab, we have a very good understanding of that. And once the device is realized, it really is extremely well captured by the device Hamiltonian that we really well understand. So this is an exercise that we can do. And so we can say like, okay, so what is the Hamiltonian behind this metapotential? First, we will need some nonlinearity. That shouldn't be too surprising. To encode a qubit, we need nonlinearity. And the nonlinearity that we need is known as a Kerr nonlinearity, hence the name Kerr-cat. And it takes this value with k is the Kerr constant. And that's extremely easy to realize in superconducting quantum circuit, because that's essentially the Hamiltonian of a Transmon qubit. And so what I'm saying here is that in this cavity, we will add a Transmon qubit, a single Transmon-like object. That Transmon will not be used to encode quantum information. Its role is only to give a little bit of nonlinearity, of Kerr nonlinearity to the field. Okay, that's important. Yeah, the information will be encoded in the field, not in the qubit. The qubit is only there as a spectator to give a little bit of nonlinearity. The second term that I need to obtain exactly the metapotential which I drew is something which is called a two-photon drive, a two-photon pump. And that's again something which is quite very standard in superconducting quantum circuit. In fact, this type of two-photon pumps are what are used to operate what are known as parametric amplifiers, which are used in every experiment in the field. And so why is it called a two-photon pump? Well, because of this square here, it adds 2 photons at a time. Okay, and so what I find in this Hamiltonian is that the value alpha that will be stabilized is given by this ratio. It's this computation now between two things again, but rather than a pump power and damping, it's a pump power over Kerr nonlinearity. So with this, we know how to stabilize cat states completely in a completely dissipationless way. It will also be useful a little bit later to look at the full metapotential corresponding to this Hamiltonian. Rather than taking a line cut at p equals 0, it will be useful to look at the full metapotential, which looks like this. So before I gave you only a line here at p equals 0, what I'm showing now is the full metapotential. Okay, and so what we see is these two wells and this saddle point in the middle, as we expected. Okay, and so again, we will stabilize states over here. Very good. Okay, let me skip this. Okay, so that's the physics of stabilized Kerr-cats. I hope also that this picture with this metapotential will, give you a little bit more intuition also for why bit flips are difficult, why bit flips are unlikely. Because here you would really have to go over this large potential well for a bit flip event to occur. That would be a very drastic event. And so there is really very good protection against bit flips here. But again, there's no protection against phase flips. So these ideas, which were first introduced in 27 with Shruti Puri, have since been realized in the group of Michel Devoret at Yale by Alex Graham and colleagues. And for a moderate size of their cats, for alpha 1.6, they've been able to show this concept of error bias with a T1 as large as 100 microsecond and a T2 of 2.5 microsecond. So we're really happy to see that these ideas are now exist also in the laboratory. The very similar ideas were also explored very successfully by the group of Zaki Lektas at the ENS in Paris. Although here they use a different protocol, which in fact use dissipation to stabilize the cats. So it's a different approach. But again, for similar size cats, they were also able to show this very large error bias. So these are very good controllable theoretically and experimentally. Okay, so very good. So now we have these stabilized Kerr-cat qubits, and the next step is to do something interesting with these qubits. We would like now to do some quantum computation, and we'd like to think, of course, about quantum error correction. because this is how I introduced this idea of saying like, okay, can we exploit our understanding of the underlying hardware to achieve at some form of hardware efficient quantum error correction. And now what we have are qubits that exhibit strong noise bias, and this is what we would like to exploit. And these ideas have been studied theoretically before, in particular by Alexandre and Preskill. There are some names that seem to be recurrent names in my talk. Some authors that seem to be recurring authors in my talk. And so what Alexandre and Preskill have shown was that noise asymmetry can be used to increase the accuracy threshold of quantum error correcting codes. So that's very excellent news. We can use bias noise qubits to increase thresholds. And that was made more concrete in the particular case of the surface code by Tuckett, Bartlett, and Flavia more recently, where they show that the error threshold can be as large as 28% for realistic bias noise ratios. So that's quite exciting, and we hope to be able to use this with these cat-state qubits. But there is here a very important question, and that question was addressed already in this paper. Is the noise bias preserved during computation? And for that, let's look at control NOT gates. So what we have so far are qubits which in their idle state have an error model which is biased. But I really would like this bias model to be preserved by the computation. And so let's look at a control NOT gate. And let's look at an error occurring before the gate. And so let's say a Z error. So a Z error we know will propagate to two Z errors, Z1 and Z2. Of course, that's bad news. There's a propagation of error, but for this particular talk, I'm quite happy because what I see is that the error bias has not been undone. A Z error propagates to a Z error. We're happy with this. However, if you look at the operation of the gate, what you realize is that if the error occurs during the gate, things are not so simple. A Z error will propagate to an X error, and that's bad news. You've unbiased the noise, and all of these ideas do not apply anymore, at least if you want to apply a control NOT. And in fact, what was shown more recently by Guillaume and Miraili is that the CNOT gate cannot be performed in a bias-preserving manner with two-level systems. And it seems that we're in trouble here. But the situation is more positive for Kerr-Katz because Kerr-Katz are not two-level systems. We can exploit the fact that these Kerr-Katz qubits have a richer Hilbert space than simply two levels to realize CNOTs in a bias-preserving manner. Okay, and so this is what I would like to look at in this slide. So the CNOT is a little bit involved. I'll come back to that in a second. So rather than looking at the CNOT and trying to understand how this is realized in a bias-preserving manner, let me rather focus on the NOT gate, which has essentially the same physics, will have the same problem as the CNOT. But since there's a single qubit, it will be easier to understand. And of course, in a NOT gate, what I want is to flip 0 to 1. I would like to do something like this, for example. I could imagine using a displacement operator to flip 0 to 1. But that's not going to happen with these stabilized Kerr-Katz qubits because of this strong protection against T1 errors, which also prevents us to flip the qubit so easily. This is where the structure of the Hilbert space becomes interesting, because if you look at this phase space, we can use much more of this Hilbert space to start and do our operation. We can do something like this, for example. We can go around in phase space to reach, to bring 0 to 1 and 1 to 0. And so we can realize this in a bias-preserving manner, in fact, and that is because we're not restricted to only two levels. Before understanding how, or at least giving an intuition of how this is in fact bias-preserving, let me say how this is done in the lab. How do we move these blobs around. And that's quite simple, in fact. So this is the Hamiltonian that we had before with the current linearity. This one we won't touch. This is fixed by the Transmon that we've embedded in the cavity. However, this two-photon drive is controlled by these microwave tones, and this we have complete flexibility there. What we can do, for example, is change the phase of that tone in time, and changing the phase of that tone in time, if we do that slowly enough, will in fact do exactly this. It will carry the coherent state around the origin as I drew there. In this way, allowing us to do a NOT gate. And so now I'd like to give you some intuition for why this is bias preserving. We can write equations for this, but I hope that this metapotential will at least give you the basic understanding. And so again, this is the metapotential where we store, for example, a plus alpha state corresponding to our 0 state here on the right-hand side well. And so by changing the phase of the drive, what we're doing is that we are changing the axis here of stabilization and rotating it in a way which is, phase dependent, okay? So we're rotating the axis of stabilization such that effectively the potential in time looks something like this. So it is rotating. And if we are rotating slowly enough, well, we will carry that coherent state from 0 to 1 and back if we want. And why is that bias preserving? Well, I hope that you accepted that it was bias preserving at this point because it's very unlikely to jump over that big potential. Well, that large potential was there everywhere, irrespective of where was there all the time as we rotated the potential. So that bias preserving nature was carried throughout the operation of the NOT gate. This is why, intuitively, I hope this is a bias preserving operation. Of course, you can be more formal and add some equations to that. So that was the NOT gate. But now we have to look at the CNOT gate, and this is where it becomes much more involved. Because now what we need is, of course, one cat to rotate respectively on the state of the other cat. And so for this, we need multiple cavities, something which is routinely now routinely done. Where it becomes a bit more maybe frightening is when we look at the Hamiltonian that is required to do that. But at Hamiltonian, although it's large, and I won't go through all of that, that's not the goal, is well under control, and we know how to realize something like this. And that Hamiltonian is in fact built of simpler pieces, one piece which corresponds to stabilizing the control qubit, one piece which is composed of stabilizing the target qubit and doing the rotation, and one piece which is there to correct extra errors, extra accumulation of phase that we don't want as we do the gate. But the important point is that we have an Hamiltonian for something like this. And what I tried to convince you earlier is that when we have Hamiltonians, we also have devices. So we have also a device which corresponds to the Hamiltonian. And although this has not been realized, or at least reported that this has been realized in the laboratory, there's no reason to believe that this cannot be done. And so with this, I'm arriving at my conclusion. So, I mean, I think superconducting quantum circuits are a promising platform for quantum computation. We've seen this week, and there are avenues, I think, for thinking ahead for the future, how we can break this platform further. The next challenge is quantum error correction, and we need for that better qubits and better codes. This idea of hardware efficient quantum error correction, where we develop qubits and codes together, I think is very powerful and is now getting more and more traction in the field, of course. So two interesting candidates beyond the transmons are the 0-pi qubit and the stabilized Kirk-cats, and both have been experimentally demonstrated. And personally, I'm looking forward to see, as a next step, these bias-preserving CNOT gates in the laboratory. If you're interested, here are some of the papers that contain the results that I've presented today. So with that, thank you.
Okay, thank you, Alexandre. So I think we can begin questions with quite a pointed question in the Q&A. I can read it out, or you can read it yourself, but it says, why do you think Kerr-Cat qubits and other proposals have not made more progress at the systems level? And what needs to happen to displace the Transmon's dominance and keep the community's efforts from being too focused too early? This is the opinion of Mr. Anonymous Attendee.
Okay, so thank you for the question. So why hasn't this been, I mean, let's look back at the history of the field, right? When Transmon were introduced, we did not try to build 50 Transmons right away. For several years, we tried to build 1 Transmon and then 2 Transmon, eventually 3, right? And this is the approach which is being followed now with these novel qubits, and I think this is the right approach. The fact that it is now behind the Transmon doesn't mean that it will be behind the Transmon in the future, right? As we learn more and more about these qubits, we can start to integrate them in larger and larger devices. And I will say that bosonic type qubits, not the stabilized Kerr-Cat qubits that I've talked about specifically, have been shown, for example, to reach and exceed a little bit even the error threshold for quantum error correction, something which has not been done yet with the Transmon. Okay, of course, that needs only 2 of these bosonic qubits, but still, in some respect, they are more advanced than the Transmon. So what will win the race? It's not clear. And for sure, the Transmon, we can extract more juice out of the Transmon, right? Maybe the Transmon is enough. Maybe there will be some more and more discoveries, improvement that will bring the Transmon to the next level. But I think one of the points that I want to make in this talk is that it might be too early to choose a winner. I think it's still time to explore multiple options.
Can I ask a follow-up question on that? Of course, I really like that.
Go right ahead.
Yeah, what I was going to say is, I agree this is interesting. I agree we have to look at systems. But one of the things that I find is really strange about this, which you did in your talk, is you discussed the improvement of, say, T1 and T2 versus time. But the real system figure of merit is T gate over T1 and T2. And many of these qubits kind of neutrinoize themselves. So it's hard to make gates, it's hard to couple together. And what I would just say is it's just a complicated issue, but I think people have to be a little bit more about system metrics than, new qubit, great T1, T2, because clearly that's not the whole story. And,
I completely agree. I mean, my goal by presenting this particular plot of T1 and T2 is first, I have easy access to these numbers. I've been showing this for years in my talks, and I don't know, that's still an interesting information to show the improvement that has been. But I agree with you, John. This is not the end of the story. And as we learn more and more about these other qubits, we are able to add these metrics to the discussions.
Yeah, and for example, in the CAT states, I would like to know, well, what's the equivalent gate time, okay? And maybe the T1s and T2s can be good or whatever. I know there's a lot of research, but I need to know kind of more system metrics about, so we can compare these better. And it's just
I would encourage you to look, for example, at this paper, which will have some of this information. And I mean, an experimental paper by Alex Grimm also, you will see the gate time to do a NOT gate, for example. But always remember that these experiments are first realizations. We should look at them in the same way that we look at the first experiment for the Transmon. This is not the end of the road for these qubits.
Yeah, maybe I can say something. For example, I mean, I agree also with the point that John makes that, you know, for example, if you look at the GKP qubit, which is in many ways very beautiful, if you say I do a single qubit gate on that qubit, it's not so easy, right? Compared to a Transmon, it's a lot harder.
Yeah.
So you gain something and you may also lose something. And I think the jury is still out. What we just have to do it, right? It has to be realized.
Exactly. Yeah, completely.
Yeah, and just to kind of reiterate this, I think it's really interesting right now to compare qubits from a system point of view, in that do you have a protected qubit, but then you have to work harder on the gates and getting them fast? Or do you have an unprotected qubit like the Transmon, where it's kind of easier to do the gates? And I don't know the answer. I just think it's really interesting that people are looking at that. But then we have to report those numbers to make sure that we know how to compare. And again, even reporting what the right numbers are not so trivial to do. But I think
Right. But maybe what I will say is that it's important. So it's important for the field to keep these questions in mind. But in the first experiment, it might not be the time to ask that question. Let's ask this question in 2 or 3 generations of these experiments where things are under control.
I would suggest these are excellent questions to come back to in the panel discussion, the wrap-up panel. I'd like to maybe give one more chance to a different and more mathematical question, but we should then wrap up. Anonymous attendee also asks, is using the word superposition really apt for the metapotential ball? And I'll amplify on that question. What is a metapotential? I think you defined it, but it's not something you use in a Schrödinger equation. And is there actually a rigorous use of the metapotential for solving quantum dynamics?
These are all good questions, in fact. So first, so to me, I will be very honest that the metapotential is just an interesting tool to visualize what's going on. I really use this to give me intuition for the physics that is going on. But for example, these metapotential have been used very successfully to understand the physics of bifurcation dynamics in what I call Josephson bifurcation amplifiers now, JBAs. So they have real value to understand what's going on. Mark Bickman, for example, has been pushing these ideas for many years. To the question of superpositions, yes, truly there is no doubt that we are preparing superposition of these coherent states that are living in this metapotential. And this has been demonstrated clearly by the experiments. So there's no question, no doubt there. Although the metapotential, at least to me, is a tool to intuitively understand what's going on, the physics is clear. We are preparing coherent states and superposition of coherent states. And in fact, if you don't like metapotentials but are more comfortable with Hamiltonians, if my okay, it seems like there's lag. Okay, I won't show that. That will not be very useful. But there was an additional Hamiltonian that I didn't talk about, which was shown in the slide, where you would, I think, be more convinced of all things that are going on here. Okay. I think by looking at this Hamiltonian, we'll be convinced immediately that indeed you are preparing superposition. There's a simple factorization of the Kerr-Cat Hamiltonian that should be quite intuitive also.
Okay, if you would care to, that's a question sitting in the Q&A and there are several others. Why don't you, if you wouldn't mind, look at those in the coming minutes. But I would like to adjourn now and thank you again for your talk. We will take a few-minute break, mainly for technical reasons. Recording goes off, recording goes on, and we'll resume in 3 or 4 minutes.